Hello everyone, this is Mrs. Ramping coming to you from my kitchen, ready to discuss which digits in a measurement are significant. So when we say significant, there's something very specific that we mean in science in terms of our measurements about what digits actually came from the measurement itself. So in order to talk about significance, we need to discuss this idea of accuracy versus precision. So to be accurate is to be right. If I am accurate using these targets below, imagine that I am someone who is able to hit the bullseye. Accurate means that the answer is correct. We also can describe the precision of our measurements. And when we as scientists set out to do investigations, we intend to be consistent with our results. We want to make sure that we are getting measurements that happen the same way under the same conditions. Now the trick with that is if there's some source of error or I make some consistent mistake, I can be precise but not accurate. Imagine someone who was set up a little funny in their aim that hit kind of a very consistent spot on the target but wasn't actually close to the bullseye. We would maybe call them precise, but whatever error they are making is making them inaccurate. However, let's say that I hit the target very well and I did it consistently, I would be both accurate and precise. So when looking at multiple data points, as scientists, we hope that our work is both accurate and precise. Now, when we discuss precision, we're really talking about if, let's say, like if different scientists tried to make the measurement of the same thing, they should get the same result. And in order to make sure that that's the case, we pay attention to the number of digits we report. So scientists agree on a set of rules related to the number of digits based on the tools that they use. So think about taking a measurement. If I'm measuring mass, I might be using a scale. If I am measuring length, I might be using some sort of a ruler. If I am measuring volume, I could use a graduated cylinder. Whenever possible, I want to choose a tool that reports as much precision or digits as I can. So let's take a look at an example. We have two rulers here, two different tools, and they differ in the way that they report their measurements. So ruler A here reports millimeter lines, while ruler B only reports centimeter lines. So what happens then is in ruler A, we can know for sure which line the tip of the nail makes it at least towards. And what I see here, and I know with my little drawing tool it's a little difficult, but I at least make it to the third line past. Then I can kind of estimate how far in the middle that nail head goes between the third and the fourth line. So our eyes have the ability to kind of estimate tenths. So let's say that it's about 4.32 centimeters. I know it made it to the 3, and I'm kind of estimating the 2. Some other researcher might say 4.31 or 4.34, and most of us would agree that that's reasonable. Now, when we look at ruler B, I don't have that reference line of the millimeters. So when I kind of eye it up, I might say 4.3, but it wouldn't maybe be out of the realm for someone to say 4.4 or 4.2. So now the 4, I know for sure it's at least 4 something, but the 3 is the estimated digit. So in this case, because this tool had less markings, less precision within it, I get a less precise measurement. Everybody agrees on the 4, but the 0.1 position, the 10th place, might be inconsistent. So let's say that you were comparing this beaker to this graduated cylinder. If you had the option to choose which one to use, which one do you think would give the more precise measurement? Choose which one you think, and then record that in the Edpuzzle video. So when we consider that when we make a measurement, we're choosing to report the ones that are actually precise, we call those figures that count significant figures. We've also referred to them as significant digits. So I include all of the known values plus the estimated digit as significant. So in order to decide which of them count, we have a series of rules to help us decide. You will record these rules and then we will practice applying them to determine the significance of the measures that are presented. The first type of digit we can consider are non-zero integers. These ones are easy because all non-zero numbers are always significant. So when I look at this measurement here, every single digit in the number is not zero. So then every measurement that's reported is considered significant. So there are 4 significant figures within this measurement because all 4 digits are known. What this is really saying is that I know the 5, the 7, and the 8 are for sure, and the 2 is the estimated digit. Whether that is a scale that is doing it or someone reading a triple beam balance, the 2 is the estimated digit, and we consider that part of the significant measurement. So from here on out, this is where it can get a little more tricky, and we need to be careful in our decisions. Zeros can count and sometimes don't. So we're going to classify zeros based on where they are in the measurement. First, we're looking here at leading zeros, and these are only really going to apply if there's a decimal, because we don't just write random zeros in front of a number unless they're place holding for a decimal point. Because these are just giving us the position of the place, the decimal place, these zeros are not significant. They are important. Oh my, they are important. 0.00321 is a very different number than 321. But it is not part of the measurement itself. So we would start counting here. The 3, the 2, and the 1, the non-zero digits are the only ones that are significant. The leading zeros don't count as significant. Our next zero is called a captive zero because it is held between non-zero numbers. Any zero between 2 non-zero numbers is significant because we know that that's what it should be. There is no estimation until we get to the 1. So what that implies is that 0 in 502.1 is known to be a 0. They are always significant when they are between other non-zero numbers. Trailing zeros are the tricky ones. They are the ones that count sometimes, but not others. And it is based on whether you have a decimal or whether you do not have a decimal. When a decimal is present, trailing zeros always count. And they trail after the non-zero numbers. So notice here, the 1 is the last non-zero number, and this is a trailing zero with a decimal place. That 0 is there because it's the estimated digit. Someone is saying they think it is exactly on the line for the 1. So we count that as significant. So the 6, 7, 1, and 0 are all 4 significant figures. This is a captive zero. This is a trailing zero. Because there's a decimal place, we're saying it's exactly on the 3, and we're estimating a 0 in that position for significant figures. When the decimal is absent, they become placeholders. So what we're saying here, this 2 is the estimated digit. But we know it's 620 something. So you have to have a 0 there to hold the place to make it 620 something as opposed to 62. But only the 6 and the 2 are significant figures. Here, the 4 is the estimated digit because it's the final non-zero number, but we know it's about 4,000. That's not a very precise measurement, right? But that might be limited by a very large beaker or something that allows us to only report the thousandths place. So in this case, the 4 is the only significant figure in this measurement. Now, exact numbers are those that we like to call as counting numbers or part of conversions. So they would never come to play in limiting significant figures because they have infinite significant figures. So when we say 60 seconds equals 1 minute, we mean like 60.0000000 and having zeros to infinity after it is equal to exactly 1.00000, lots of zeros to infinity after it. It's an exact number. When you count things like people, I don't have like 3.2 people. I just have 3 people. So it's exactly 3. It has infinite significant figures. The last one is a way to interpret scientific notation. It also plays on a way to report the correct number of significant figures when I have a large value that I want to adjust. So all of the digits in the root number are significant. The root number is this portion of scientific notation. So whatever precedes the times 10 to the is the root number, and that is where the significant digits are. All 3 of these digits are there because it's significant. Here, the 4.35 is the significant digits, and the 7.10. So whatever they convert to doesn't matter. These are the digits that are significant within this number. So with that, you have learned all of the rules for interpreting significant digits. Now it is time to practice and do the Canvas practice that will give you some feedback on how well you can identify significant digits within measurements.